This is going to be a really brief lesson about Chapter 6.6, and the objectives here are to understand the methods for approximating the area underneath a function. And we have done this before in the past. We used rectangles. And I'm going to review that briefly, and then what we're going to be doing is really quickly looking at what we call Simpson's rule and the trapezoidal rule. And these are just two more different kind of formulas that we can use to approximate the area underneath a function. To begin, we're going to review how we used rectangles in the past to approximate the area underneath a curve. So this is actually, we're going to look at something similar to problem number 7 in your homework assignment. But this is an integral, and remember, an integral, and this is a definite integral bounded from 4 to 9, is just another way of setting up or notating to us that we want to find the area bounded by this square root of x, 4, and 9. With that said, they give us also this n equals 8. And remember, in terms of our notations, n is typically some sort of number that we're dividing that interval up into. So we're saying that we're going to divide this integral, or this region, from 4 to 9. So here we have it, from 4 to 9. Into 8 different pieces. So you're going to have something that looks like this. And when we were doing rectangles, we would specifically divide 4 to 9 into 8 equal portions. And what those equal portions were, they were widths of these rectangles. So I'm going to quickly add that each space in between here, there's a delta x. All right, that's this width right here. This width right here of that rectangle is also delta x. This width is also delta x, and so on and so forth. So all of these are our delta x's being the widths of these rectangles. And I am going to also be doing what we called in 6.2 an upper approximation, or upper sum. You can see what I used was these right hand kind of endpoints, or these right hand sub parts of this interval, and that formed the height of these rectangles. That there's a little bit of excess on the outside. That's why we call it an approximation, and that's also why I'm going to call this an upper sum, because it's going to be slightly over than the actual area under this curve. But then what we did was we used this Riemann sum right here, and what this Riemann sum actually does is it's going to be saying, well, let's look at the first rectangle. The first rectangle would be given by the height, so f of some sort of c sub I, and we're going to calculate those here in a little bit. But it's the height times the width of the first rectangle, plus, that's what this summation is, the height times the width of the second rectangle, so f of c sub 2 times delta x. And of course, all the widths are going to be the same, but these heights are going to be changing as we go along the way. So what I really want to be figuring out is, what is this c sub I? Or in other words, what are these x values as we move along these sub intervals that we broke this interval into? So delta x is going to be determined by 9 minus 4, so 9 minus 4, the upper minus the lower, all over the number of specified n parts that we want to break this into. And then what I said was, oftentimes how we calculate x sub I is going to be delta x times I. So you're going to take what you have here and multiply it by I. And then in this case, the c sub I, we just have to be very careful. C sub I isn't just going to be x sub I. It's going to be, consider what is this x value? It would be 4 plus and then our x sub I. This x value that we're interested in, that would indicate this height of this rectangle, this x value, so this f of x sub 2, what we would be most interested in was not only 2 delta x's, but 4 plus 2 delta x's. This x sub 3, that would notate our height of our third rectangle, so this f of x sub 3 right here could be calculated by 3 delta x's, so delta x times I, but then 4 plus, and then this delta x times 3. So this is what we're going to be using. Alright, so this is all of our information. So finally, what I'm just going to say is start writing this all out. So we do know that x sub I would be equal to our delta x times I. and then c sub I would be equal to 5i plus 8. So right here, what we're going to eventually do is calculate this sum would be equal to, we would have to first calculate f of, and then c sub I, which would be 4 plus, and then 5 times 1 of 8, because we're going to start at the index 1 and work ourselves up to 8. So it would be the square root of f of, what goes in for x would be 4 plus, and then this right here is what we're interested in, x sub 1. That's going to be the first height of our rectangle that we're interested in. So 4 plus 5 over 8 times, and then we need our delta x, so 5/8. Okay, that would be our first piece of this summation formula. Then we're going to go on to our second term, which is going to be f of c sub 2, because we want our second term. So we would have to go into this equation and plug in 4 plus 5 times, and then 2 over 8. So we're going to go into our x and plug that in. Oops, that's an 8. And then times 5/8. Okay, and then plus, we're going to go on our third term, so f of c sub 3. So we're going to have to go ahead and figure out what would c sub 3 be. We're on this height of our rectangle. That's the height that we're interested in. So we're going to be plugging in 4 plus, and then 5 times 3, so 15/8. And then times the width of this rectangle, which of course is still 5/8. And we're going to be doing this all the way up to, I'm just going to say dot dot dot, plus our very last term is going to be up until the 8th, because that's how many terms that we've separated into it. So it would be x sub 8. And then how we would figure out that height is we would plug in this c sub I in for our x. So it's going to be finally, and I'm going to write this under here, 4 plus, and then 40/8 times, and then once again the width. Alright, so rectangles is what we have used in the past. We used rectangles to try, what we would do is use these Riemann sums to sum up the heights times the widths of all these rectangles along a certain interval that's been specified by a definite integral. But now what we're going to be using are two different rules. One's the trapezoidal rule. Here that is, and it is also in your books on page 445, and they have a proof on page 444. Please look over the proof. Please look over how the trapezoidal rule, why and how it works. It's the same idea as drawing a bunch of different rectangles, except you get a closer approximation, and it does look a little bit confusing here, but really in the next video I hope you can see it's very straightforward. So please look over page 444 and why this exactly works. But once again, the trapezoidal rule is just another way of approximating the area underneath a function. The Simpson rule, that's found on page 447. You'll notice just a slight difference, and it's the alternating of 4, 2, 4, and then 2 of all the inner functions that you're adding up. And then on the outsides, there's just 1 times f of whatever c sub I or x sub I that you're looking at. So once again, these are going to be kind of plug and chug formulas, and they're tedious to calculate out. I am going to warn you at that. And so does I hooked a YouTube video of another guy doing the Simpsons rule. He warns the same thing, that it's tedious. Algebra, really. You just need to use these formulas to basically plug in the information that you're looking at. Tune into the next videos for actual examples of these two different rules.